Welcome back to Control System Lectures. This video is a continuation of the series that we've been doing on approximating Bode plots by hand. We're going to wrap up this topic for now with this fourth and final video. At the end of this lecture, you should have all of the necessary tools you need to approximate the frequency response of any transfer function. We've already covered transfer functions that are constants, which is a transfer function that has no poles or zeros. And we've also covered transfer functions that have a real pole or zero at the origin. And the last video covered transfer functions that have real poles or zeros that aren't at the origin. So far, all of our discussions have been about poles and zeros that lie somewhere along this real line. None have ventured out into the imaginary realm, until now. In this lecture, I'll explain how to draw an approximation of the Bode plot by hand for a function with a pair of complex poles or zeros. And by pair, I mean two poles or zeros that are symmetric about the real line. In other words, the imaginary component have equal magnitude but opposite signs. So why a pair and not a single complex pole or zero? Well, I'm glad you asked. Let me explain it this way. A transfer function with a single complex pole might look something like this. 1 over s plus j. And this function has a single pole at s equals minus j. And mathematically, this is a perfectly legitimate transfer function. However, we need to remember that transfer functions aren't just mathematically abstract functions. They represent real physical objects. And so now the question is, what physical first-order object could this complex transfer function represent? I'll give you two quick examples. A first-order mechanical system could be a massless spring damper system, with spring constant k and damping coefficient b. And the transfer function could be written like this. And now in order for this transfer function to have imaginary roots, either the damping coefficient or the spring constant has to have an imaginary value, which for a physical system doesn't make sense. If we take an electrical example, we could have a circuit that has an inductor and resistor in series, where the inductor has inductance L and the resistor has resistance R. And the transfer function for this first-order system would look similar to the mechanical system. It would be 1 over Ls plus R. And now we're left with the same problem. What does it mean to have an inductance or resistance that has an imaginary value? Now something to think about here is, what would a physical system look like that had an imaginary value for one of its properties? So in both of these cases, the coefficients of the transfer function polynomial all have real numbers. And that's because they represent real physical values like spring constants and inductance and resistance. Other physical properties are things like torque or pressure or flux or current or volume, and all of these have real values. Even if a transfer function has polynomials that have real coefficients, it's still possible to have imaginary roots. But in order to do so, we must have a second-order system or higher. This can be seen from this generic second-order equation. You can solve for the roots of this equation using the quadratic equation, which is minus b plus or minus the square root of b squared minus 4ac all over 2a. In order to have complex roots, the value inside the square root must be negative. And you can see that this is true when 4ac is greater than b squared. And if we took the ratio of these two, you could say that when the square root of b squared divided by 4ac is less than 1, then we'll have complex roots. This is called the damping ratio, and it's assigned to the Greek letter zeta. This ratio is important in control systems since it marks the boundary between complex roots, i.e. oscillatory motion, and real roots, which is exponential motion. So let's continue on with our idea. Let me rewrite the quadratic equation in this form. You can see that the right side of the equation could be either real or imaginary, based on the damping ratio zeta, but the left side of the equation is always a real value. So now you can see that if we have complex roots, the real portion will be the same for both roots, and the imaginary portion will have the same magnitude but opposite signs of each other. And these are called complex conjugates. We can show this graphically on a real imaginary axis like this. The two complex roots will always be mirror images of each other across the real line. And this is why for real physical systems, complex roots will always come in pairs and always be complex conjugates of each other. Now that we have that understanding, let's get to the math and learn how to draw the frequency response of a system whose transfer function have two poles that are complex conjugates. The form of this type of transfer function could be written like this: omega naught squared divided by s squared plus 2 zeta omega naught s plus omega naught squared. But like we did in previous videos, we want to manipulate the form into this structure by dividing both the top and bottom by omega naught squared. At this point, solving for the frequency response is no different than for simpler transfer functions. First, you have to substitute s equals j omega, and then solve for the real part and the imaginary part of the equation. The only difference here, though, is that this equation is a bit more complicated than the previous ones we looked at, so the algebra can get a bit unwieldy. I assure you, though, I'm performing the same mathematical steps that I did in previous videos. I always recommend you trying this on your own, though. 1, to verify that my math is correct, and 2, practicing it helps you to retain the knowledge. The white bit at the end here is multiplying the top and bottom by the complex conjugate of the denominator in order to move the imaginary number j to the numerator. And once you've multiplied those equations together and you separate out the real component and the imaginary component, you should end up with two giant equations that look similar to these. And now if these haven't scared you off, then we can use the real and imaginary components to estimate the magnitude and the phase across the entire frequency spectrum. We'll start by drawing our empty Bode diagrams, one for gain and one for phase, and then we'll mark in the middle here somewhere where our break frequency omega naught is. And as you're used to by now, we'll break our estimation up into 3 different cases. The first where omega is much smaller than omega naught. In this case, omega over omega naught goes to 0, and the real part simplifies just to 1. And for the imaginary component, it can be approximated as 0, since the numerator goes to 0 when omega is really small. Now the magnitude of h of j omega is just 20 times the log base 10 of the square root of the real component squared plus the imaginary component squared, which turns out to be 0 decibels. And we can just draw this in on the gain plot up to the break frequency. Remember, this is just an approximation, not an exact plot. For phase, it's the argument of h of j omega, which is the arctangent of the imaginary part divided by the real part, which is just 0 degrees up to the break frequency. The second case is when omega is much greater than the break frequency. In this case, omega over omega naught dominates the equation, and the real component can be approximated as omega over omega naught to the negative 2 power. And the imaginary component can be approximated as 2 zeta omega over omega naught to the negative 1 power. To find the magnitude, note that the real component is much smaller than the imaginary component because it has a square rather than a single power. So as omega gets larger and larger and larger, the magnitude is going to follow the trend of the real component, which is minus 40 dB per decade. So we can draw that line in starting at the break frequency. As for phase, I made a mistake here in my intermediate step, but it's too difficult for me to go back and correct it at this stage, so I'm just going to have to leave it for now. But the phase at these higher frequencies does come out to be minus 180 degrees, so we can draw that in starting at the break frequency. For the third case, omega equals the break frequency omega naught. Now the ratio omega over omega naught equals 1. The real component is 0, and for the imaginary component you're left with minus 2 zeta divided by 2 zeta squared, or just minus 1 over 2 zeta. Now for the gain plot, this is worth noting. The magnitude at the break frequency is equal to 1 divided by 2 zeta written in decibels. In other words, as your damping ratio decreases, your magnitude at this break frequency increases all the way up to infinity when zeta goes to 0. Notice that for zetas larger than 0.5, this magnitude is going to be less than 0. For that reason, for the approximation, we generally only draw a peak when zeta is less than 0.5. Phase, however, is slightly more tricky. At the break frequency, the phase goes to minus 90 degrees, which is halfway between. However, the slope of the line that connects the blue line to the pink line changes as a function of zeta. Now you can either look up the shape of the graph in a chart based on your zeta, Or you can draw it directly by drawing a line starting at omega naught divided by 5 to the zeta power, all the way up to omega naught times 5 to the zeta power. Now these three line segments for the gain and phase plots are just approximations of what the frequency response looks like. The thick red line is the exact frequency response of the system. And you could draw this closer by just smoothing out the lines. However, generally what you're trying to find is the low frequency, high frequency, and break frequency characteristics, which you can just do with a straight line approximation. Now I've spent this entire time talking about complex poles. But just like we did before, we can approximate the frequency response of complex zeros by noting that a zero is 1 divided by a pole, and on a log-log scale of a Bode plot, this is just the negative of a complex pole. So you can just reflect the response about the horizontal axis to get the response of a zero. And this wraps up the segment on approximating Bode plots by hand. I apologize for the messiness and confusion at the end here, but I hope that you have enough information to at least attempt this on your own. Being able to approximate a Bode plot goes beyond just being able to draw some lines on a graph. You should be able to understand how adding a pole or a zero to a transfer function changes the frequency response characteristics of a system. This skill is invaluable when designing something like a PID controller or adding a filter to a signal to remove unwanted noise. And so while you may never actually draw a Bode plot by hand, you will always benefit from knowing how. Thanks for watching, and don't forget to subscribe.